Welcome. Today, we explore the profound journey of a scientific pioneer whose bold ideas reshaped our understanding of the molecular world. This slide, titled Courageous Questioning, introduces us to the life, epistemological battles, and enduring legacy of Hermann Staudinger. Set against a vintage backdrop of technical schematics and handwritten notes, Staudinger's portrait stands alongside a striking red geometric line that symbolizes the sharp, disruptive path of his paradigm-shifting ideas. He dared to challenge the scientific status quo of his era, facing fierce skepticism to prove the existence of macromolecules, the very foundation of modern polymer science. Join me as we delve into the story of a man whose relentless pursuit of truth changed chemistry forever. In this slide, titled A Singular Vision That Built the Modern World, we look at the monumental shift in chemical history. Before 1920, complex materials were dismissed as mere grease chemistry, assumed to consist only of small, simple molecules. Hermann Staudinger bridged this profound gap. Awarded the 1953 Nobel Prize in Chemistry, he fought a decades-long battle against the scientific establishment to prove the existence of macromolecules. Below the historic laboratory and natural rubber imagery, a red polymer chain weaves toward the modern era. Today, both our biological world, like the DNA helix shown here, and our synthetic world, represented by advanced plastics, fibers, and aerospace components, are entirely understood through his revolutionary lens of giant chain molecules. This slide, titled The Making of a Classical Master, traces the early foundations of Hermann Staudinger's brilliant career. In 1899, the aspiring botanist pivoted to chemistry at the urging of his neo-Kantian philosopher father. By 1905, he discovered ketenes, highly reactive gases that would later become crucial synthetic intermediates for antibiotics like penicillin and amoxicillin. Most famously, he developed the Staudinger reaction, which combines an organic azide with triphenylphosphine to yield iminophosphorane and nitrogen gas. A century later, this exact reaction serves a revolutionary modern purpose. It forms the foundation of bioorthogonal chemistry, which scientists use to safely track molecules inside living cells. This slide, titled The 1920s Establishment, Grease Chemistry, illustrates the fierce scientific dogma Staudinger confronted. In this era, the prevailing rule dictated that molecules over 5,000 molecular weight simply did not exist. The scientific consensus, led by prominent chemists like Emil Fischer, Carl Harries, and Heinrich Wieland, argued that high molecular weights were merely apparent values caused by the physical clumping of small particles. As shown in the aggregate or micellar theory diagram, these clusters were thought to be held together by weak secondary forces. This rigid mindset is perfectly captured in Wieland's direct quote to Staudinger, urging him to drop the idea of large molecules and simply purify his products to prove they were low molecular compounds. This slide, titled The Radical Shift, Uber-Polymerization, captures the pivotal 1920 breakthrough that fundamentally redefined chemistry. Here, we see Staudinger's core assertion: polymers are not loose aggregates, but giant, single molecules comprising hundreds of thousands of atoms bound by strong primary covalent bonds. The slide illustrates this concept using a simple, powerful analogy. On the left, a scattered pile of paperclips represents small constituent parts, such as isoprene monomers. Through covalent bonding and catalytic reactions, these individual pieces physically link together into a continuous chain, forming a true macromolecule, like polyisoprene or natural rubber. Below, the chemical diagrams map this exact molecular transformation, visualizing the birth of modern polymer science. This slide, titled The Great Chemical Divide, maps out the historic clash between two competing scientific worldviews. On the left, the scientific establishment fiercely defended the aggregate theory, insisting that structures were merely clusters of small, distinct molecules held together by weak physical forces, with molecular weights never exceeding 5,000. Conversely, Staudinger's visionary macromolecular theory proposed a radical alternative. Giant, continuous molecular chains locked together by strong, primary covalent bonds, soaring in weight from 10,000 to the millions. While the establishment dismissed colloids as a simple physical state of aggregation, Staudinger recognized them as single, massive molecules, a defining shift that ultimately birthed modern polymer chemistry. This slide, titled The Proof, The Elegance of Rubber Hydrogenation, details the decisive 1922 experiment that shattered the establishment's dogma. Aggregate theorists assumed that unsaturated double bonds generated the weak forces holding natural rubber together. To test this, Staudinger and Jacob Fritsche hydrogenated natural rubber, eliminating those double bonds entirely. If critics were correct, the weak forces should have vanished, reducing the rubber to a low viscosity liquid. Instead, the actual result proved undeniable: the hydrogenated rubber remained a high viscosity, non-distillable colloid. The structure survived. This elegant test provided definitive proof that giant molecules are locked together by indestructible covalent bonds, rather than weak attractive forces. This slide, titled "A Dual Front War, Intellectual and Political Defiance," details the immense institutional and political battles Hermann Staudinger faced. On one front, he defied the chemical establishment. Mocked at the 1926 Dusseldorf debate, titans like Emil Fischer and X-ray crystallographers dismissed his work, derisively labeling it grease chemistry because they insisted small, unit cells proved molecules were small. On the second front, Staudinger fiercely defied German nationalism. He protested World War I poison gas usage, clashing bitterly with Fritz Haber, faced Gestapo denunciation for pacifism in the 1930s, and resisted intense pressure from Nazi-aligned university rectors like philosopher Martin Heidegger, who actively attempted to oust him from his position at Freiburg. This slide, titled "The Stubborn Conviction of a Rebel," captures the defining defiance of Hermann Staudinger. Enclosed within a symbolic red molecular chain, the central declaration, "Here I stand, I can do no other," marks the moment Staudinger controversially quoted Martin Luther to defend his macromolecular theory. Delivered during a highly hostile farewell address at ETH Zurich in 1926, these words epitomize his absolute conviction that organic chemistry's classical laws fully applied to the giant molecular scale. Refusing to yield to either the physicalists of the scientific establishment or the pressures of the political regime, Staudinger stood firm, embodying the unshakable spirit of a true scientific revolutionary. This slide, titled "The Chain of Evidence," charts the multidisciplinary validation of macromolecular theory between 1922 and 1935. It outlines 4 definitive pillars of proof that silence the skeptics. First, the 1922 chemical proof showing intact covalent bonds via rubber hydrogenation. Second, the 1927 physical proof where X-ray diffraction demonstrated that molecular chains extend far past the traditional unit cell. Third, the 1929 mathematical proof, Staudinger's law of viscosity establishing a direct correlation between viscosity and chain length, and finally, the 1930 synthetic proof, where Wallace Carruthers at DuPont synthesized nylon and neoprene. Together, these milestones built an unassailable case that permanently cemented Staudinger's revolutionary theory. This slide, titled "The Biological Frontier and the Ultimate Partnership," highlights a profound convergence of love and science. In 1928, Staudinger married Magda Voigt, a brilliant Latvian plant physiologist and biologist. Magda became his closest intellectual collaborator, bridging the gap between synthetic polymer chemistry and cellular biology, visually represented here by their portrait blending directly into a living cell diagram. Together, they looked toward the ultimate frontier of macromolecular science. Long before the discovery of the DNA double helix, Staudinger remarkably hypothesized in 1936 that every gene macromolecule possesses a quite definite structural plan, which determines its function in life. Their shared vision laid the groundwork for modern molecular biology. This slide, titled "Vindication," the 1953 Nobel Prize, marks the ultimate triumph of Hermann Staudinger's career. At age 72, he was awarded the Nobel Prize in Chemistry solely for his discoveries in macromolecular chemistry. Arriving a full 33 years after his radical 1920 paper, this historic milestone finally recognized him as the undisputed father of modern polymer chemistry. Framed by a golden Nobel medal and a red molecular chain, the slide features a poignant quote from Arne Fredge's presentation speech, reminding us that the development of macromolecular science was not a peaceful idyll, but a hard-fought battle. This award stands as the definitive vindication of his brilliant, lifelong scientific rebellion. This final slide, titled "The Blueprint of the Modern World," illustrates the profound, dual legacy of macromolecular theory. A single molecular chain splits into 2 pathways, representing how this discovery transformed our physical reality. The upper path shows how understanding macromolecules enabled the targeted engineering of synthetic polymers, giving rise to plastics, synthetic fibers, and a modern materials revolution in aerospace and manufacturing. The lower path reveals the biological frontier, providing the structural framework to decode life itself by proving that biology is driven by the masterly architecture of giant macromolecules like DNA and proteins. Ultimately, Staudinger's courageous questioning proved that whether in a plastic bottle or the human genome, the blueprint of reality is written in the chain.